Well, see, part of Tiara's head. You're not smiling like you were yesterday.
Yeah, it's Thursday.
Up and down. Should be better. This- Thursday's better than hump day.
No, I could barely get up because this is the only class I have today.
Okay. I'll try to make it entertaining. I got Alexis. I got Dion. Ooh. Now I think I have Deborah. Okay, I think we're all here. Guys, I was looking at what we had done in the last section. It's important. I don't know how much of the homework you've worked on, but I'm going to do a little recap of everything I've done and the most important theorems. And I got in a hurry to end the class yesterday, so I'd like to go over that again. And I would I'll just add, probably won't have much time to add anything. Well, I have a little bit, add a little bit new today. Don't forget that sequences quiz is due, and this 11.2 section is really important. It's long, it's been long, and I want to make sure that that everybody understands the stuff in 11.2. That's why I'm going to kind of go over it again today. We'll go on to something again tomorrow, but you need to make sure, if you hadn't done the homework, to catch up with the homework. And then I'll take questions today as well. Okay, see what I can get up here. Okay. Okay. So, has anybody tried some of the homework on this from it started really with the telescoping series stuff. Has anybody tried any of that yet? Yes, no, maybe. If you've tried it, raise your hand. Okay. Don't get too far behind with this stuff. Everything depends on everything else in this stuff. So I'm hoping we'll use this weekend to sort of catch completely up. It won't be long before we have another test, and you don't want to find yourself behind on this. But I'm going to do a complete recap of this section 11.2. The thing you're going to be having the quiz on is actually section 11.1. So that's just the sequences, taking the limits of the sequences and writing out sequences and recursive sequences. And I did put a couple on there for you to see if you could come up with the nth term for the sequence, that where we had to see the pattern and kind of write that. They were very similar to the ones that I did. So if you look at the notes that you took for those, it should look similar. All right, let's take a look at what we've done so far. And I'm gonna bring out the highlights here and the kind of stuff we're gonna need to use in the future. So so one of the first things we did in this section was look at telescoping series. And I picked one out of the homework to do, so you might want to pick the next even one or something to try. We wanted to know whether this series converged or not. And what that means is, does it have a sum? And what that means is, does the sequence of partial sums, Sn, have a limit? If you look at it like we did this one, and actually in this, also in this homework, they ask you to write the first three partial sums. So if I let S1 be 1, it'll just be 1/3. I'm going to take two of them, one of which I've already got, to find S2. So the next one will be 1/4 times 2 squared minus 1, and that's 1/3 plus a 15th. The third one will be those first two plus the next one. If you plug in 2, you'll get 4 times 4 is 16 minus 1, you'll get 15 in the bottom. So that's S3. Now, it's a little hard to see where that's going. Even if you put it in decimal form, you might not be able to see where it's going. So one technique we had was trying to see if it was a telescoping series. And essentially a telescoping series was where something sort of collapsed in the middle and the Sn was something you could take the limit of. If you do that, then you'll get the sum. So what I did on this one, and I'll let you look at the details later when you're looking at it. But what I did on it was I took the AN, in other words, this thing right here, and I tried to see if I could use partial fractions to rewrite it. And I did that, and it turned out that there was a half for A, and minus a half for b. So when I see this kind of setup right here, I'm thinking maybe things will subtract out and drop out eventually, particularly when I'm finding one term after the other. Also, one thing you can do with a series, because a series means to add all things together, there's going to be a half in every one of these. So I can pull the half out of a series right there. It's sort of like an integral. If you remember what we did with in Calc 1 with area, where we were summing up rectangles, that's sort of like this. All right, you can pull that half out because it's going to be a half in every one of those things. Now what I want to do is start to see if I can write the series here. And I'm doing it from this piece right here. I did the 1/2, so the 1/2 is right there. And then I started looking at these two pieces. So for instance, if I said these two pieces, let n equal 1, I'd have 1/2 minus 1, which will be 1/1. The next one, if I put in 1 here, will be 1/2 plus 1, which will be 1/3. So that one right there was when I plugged in n equal 1. Is everybody okay with how I'm plugging things in? All right, I moved to 2. If I put in 2, it'll be 2 times 2 minus 1 will be a 3 down there, so I'll have 1/3. And if I put in 2 here, it'll be a 5. So the next one I get is 1/3 minus 5. So I'm doing this sum. The next one, if I look at 3, I'll get 2 times 3 minus 1, which is 1/5, minus 1/2 times 3 plus 1, which is 1/7, and that's S3. And then I didn't go much further, but you'll notice if you go to 4, you would have twice 4 minus 1, which is 1/7, and then the next one's going to be minus 1/8. What happens here is this. That's what you're looking for in a telescoping series. Because if you regroup them, you can see that you can cancel that. And then you can cancel that. And then you can cancel those. And actually, the plus is the last thing that gets canceled out of anything. So the one right before, that's the plus one. So the one right before that one cancels that one out. Okay. So what's left in the end is this 1 minus 1/2n minus 1. If I take the limit as n goes to infinity of that, and I really should have written that there, not just write that, that's Sn. If I take the limit of that Sn, all right, what I wind up with, that clearly is going to go to 0 right there. We'll have the 1/2 times the 1, which is 1/2. So if we were to go back and look at this sequence of partial sums here, guys, right, let's see, right here, if we were to go back to where we were writing those things out, basically if you found enough of those, you would see that those sums were getting closer and closer to 0.5. But we actually found a way to do it because this series, or find the sum, because this series was a telescoping series, and we could do it that way. Okay, so that's what the first problems in your book say, all right, see if you can write this as a telescoping series. You're going to try partial fractions on it and hope that things drop out. And that's what happens.
I have a question.
Yeah, Alexis.
So, like, if you put this on a test, like, are you going to say it's a telescoping series, or like we just have to?
I'm going to tell you this. Eventually, we're not going to worry about what the sums are. We're only going to worry whether it converges or diverges. And actually, because it's really hard to find a sum. So if I ask you to find the sum of something, it's either going to be a telescoping series or a geometric series. Those are pretty much the only two choices you've got. And this one clearly isn't geometric. I'll do some geometric in a minute and you'll see that, okay? So you'll know if I say find the sum, you'll say, oh, well, that's telescoping or geometric. Check to see if it's geometric, which you will see it's not. Then you know it's telescoping, okay?
And also, like, with this stuff, like, I guess with the telescoping, like, is it is it a way we know it's telescoping when we do partial fractions?
Yeah, you do. Yes. Yeah, that's probably the only time you'll see partial fractions in this next stuff we're doing. When you can do partial fractions, it has the chance of being. See how it turned out to be this thing minus this thing instead of just one whole this thing right here. When you see that happening, or when you can do that with partial fractions, you got the potential of having this two terms, a bunch of which are going to drop out. Okay, that's what happens there. And yeah, this is probably the last time this semester we'll use partial fractions, but that's a good thing to use it on here. Okay, good questions. Anybody else? Other question? Okay, so that's kind of the first thing we did here. The second thing we did, and we did a little proof of this yesterday, but we found out that the series 1 over n is divergent. It's got a special name. It's called the harmonic series. If I were to write terms of it out, it would look like 1 plus a half, plus a third, plus a fourth, and so on. That series right there diverges. It is called the harmonic series, okay? We'll show another little proof of why it diverges a little later, but the proof we showed earlier was that you could kind of group things and you always got halves, and you can make an infinite number of halves as big as you want. Okay, so you want to keep that one in your pocket. That's going to be important. Every time I say harmonic series, that's going to be in your head, and the fact that it's divergent. The next thing we did was geometric series. So the geometric series have a very special form. Remember, it's when you have a first term and you get the next ones by multiplying every time by the same number r. So what it looks like in this sigma notation, this summation notation, is a times r to the n minus 1. These would be the terms of that. Important things about this: it will converge if the absolute value of r is less than 1. And if you identify a and r, you will have the sum. You will have the sum of that geometric series. It will diverge when r is greater than or equal to 1. And there is no sum. If it diverges, that means its limit of sequence of partial sums is going to infinity. Okay, so let's practice a couple of those. And I grabbed some of these right from the even problems of the book, guys, so they should be so your homework should look very similar. All right, let's look at the first one. I wrote out the series first, but suppose we were just given this, and we said, well, is that a geometric series? Sometimes it really helps to put in some values of n and look at it, because if you take a look at it, you can kind of see if you can go from one to the next and what r is. So for instance, if I let n be 1 here, it'll be e over 3 to the 0. The next one which will be 1. If I put n equal 2n, I'll get e to the first over 3 to the first. If I put 3n, I'll get 3 minus 1 is 2, so that's e squared over 9, and so on and so forth. So here's what I want you to look at, guys. The question then, it's geometric if you can start and go from one to the next by multiplying by the same thing every time. It's called the ratio, okay? So what's my a in this one, guys? What do I start with?
1.
Yeah, a's 1. Exactly. That's the first one. So a's 1. And it's not a bad idea to look to see what you would, if you got 1, it makes it particularly easy. What would you have to multiply 1 by to get e over 3?
E over 3.
E over 3. And then you say, well, then maybe r is e over 3, and you'll check the next one. E over 3 times e over 3 is e squared over 9. And then so on and so forth. So what you find out here is that a is 1, and r is e over 3. R is e over 3. Okay? So it is geometric. Now the question is, does it converge or diverge? In other words, does it have a sum or not? And the conditions for that were what, guys? When did it converge? Look at my condition up there. When did it converge?
When r is less than 1.
When the absolute value of r is less than 1. And it diverges when the absolute value of r was bigger than or equal to 1. So tell me what about e over 3? Bigger than 1 or less than 1?
Less than.
Less than.
Yeah, less than, because e is only how much? 2.71828. So we get 2.71 over 3. That's actually going to be convergent. So this one right here converges. It's pretty easy if you know what R is. Now the sum will be A, which is 1, over 1 minus R, and R is E over 3. And then if you do some work on that, you can find a common denominator and invert and multiply. It'll be 3 over 3 minus E if you simplify that. But it's A over 1 minus R. And A was 1. That's A over 1 minus R. So that's what the sum of this is. If you were to write those out and do successive partial sums, it would be getting closer. The partial sum would be getting closer and closer to that sum right there. Okay, everybody okay? All right, let's look at the next one. This one looks kind of funky. And it's not real obvious what's going on here because I've got this -5 to some powers and I've got that 4 to powers. This is where it's really handy if you'll write out a few of these terms and see if you can see what's happening. So I'm going to let n be 1, and that would make that -5 to the 0. So that's just 1. If I let this be 1, it'll be 4 to the -1, so the first term is 1/4. If I let n be 2, 2 minus 1 is 1, so I'll get a -5. 4 to the -2 is 1 over 16. So the next one I get, and I'm just going to leave it unmultiplied because this really might help. So it's going to be 5, the minus coming from the odd power here, over 4 to the -2 is 1 over 4 squared. So there's that one. The third one is going to look like 3 minus 1 is 2, -5 squared is 25, over 1 over 4 cubed. It's going to, now you can see the signs jumping around now, and that's exactly what's going to happen. And you don't need a whole lot of them to see, guys. Can you tell me what A is in this one?
1/4.
Yeah, it starts at 1/4. Okay. Can you tell me, anybody, what R is? What do you do to get to the next one every time?
-5/4.
Yeah, guys, since it alternates, you do need it to be negative. So to get a 5 from that 1, it'd be 5, and then you got one more 4. If you look at this one, does it work? Well, -5/4 times that one will give you 25, and it'll give you another 4. So R is -5/4. And we said A was 1/4. Now, notice up here in my conditions, it says it diverges when the absolute value, and that's important here, the absolute value is bigger than or equal to 1. Well, if I look at the absolute value of that, it's 5/4, and 5/4 is certainly bigger than 1. So what that says is that that one diverges. Okay, everything diverges. I mean, that one diverges, sorry, because the absolute value of the R is bigger than 1. And we showed that that depended on a property that we proved in section 11.1 about when limits existed of R to the nth power. All right, let's do another one. Look at this one. Sometimes they're a little funky, and you might need to kind of look down in the series to see what's happening. But it starts out with these 2 whole numbers here, and then it goes to 1/3 minus 1/9. What do you think the next one's going to be? If you're just following the pattern you see at the very tip end of this thing, what do you think the next one's going to be?
1/27.
Yeah. What I hear it. 1 over 27. So I think that's going to be 1 over 27. Now, again, here's a way to look at these things just to sort of test yourself here. What did you don't look at those yet, but look at this one. What would you get to go from here to here? Multiply by what?
-1/3.
What, -1/3, and the next one will be another -1/3, which will give you the 1/27th, and a -1/3. But then you got to explain what's going on here. Well, does the -1/3 work there? Well, look at 3. If that's my A, 3 times -1/3 does give me -1. And then -1/3 times -1/3 times -1 gives me +1/3. So if you could catch the pattern as you go down to the end and check that it works all the way across, you see you've got you got a geometric series there. The R here is, I mean, the A here is 3, and the R is what you guys said it was minus 1/3. All right, is it going to converge or is it going to diverge?
Converge.
It's going to converge because the absolute value of R, 1/3, is less than 1. And the sum on this one will be A, which is 3, over 1 minus R, which is minus 1/3. And you do take the R out of absolute value when you're finding the sum there, guys. So that's 3 over 4/3. So it'll be 9/4 or something like that. Okay, just simplify it and you'll see what the sum is. But that's what you're checking for. Now, there's a really interesting problem in your book that I want you to look at, and I'm going to scroll down and see if I can find some empty space here for a minute. I want to show you what. Actually, this is enough empty space right here. There's a problem that says somebody drops a ball, say from some height, and it bounces on the ground, but every time it bounces on the ground, it just jumps up not quite as high. That's usually what balls do on Earth, okay? So if you think about it, it's just bounce, 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 bounce. What the problem asks you to do is to see if these bounces make a geometric series. And if they make a geometric series, what's the sum of these bounces? In other words, how far does the ball actually go? How far here, 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 here? If you can add that up, you might be able to do the problem. I think it's number 55, but look at that one because that's an interesting application of a geometric series. All right, I'm gonna get rid of that. I think it's 55. You'll see it if you look at your homework. Okay, so those are geometric series. So the next thing we did was something called the nth term divergence test. Now what that says is, given a series AN, if the limit as n goes to infinity is not 0, in other words, if the tail end of this thing is not going to 0, then it's divergent. It diverges. There's nothing you can do to stop it. It is going to diverge. You're not going to have a sum there. Sequence of partial sums is just going to get bigger and bigger, which kind of makes sense because you want the nth terms to get smaller and smaller if you think it's going to add up to something. In the second piece here, it says, what if the limit as n goes to infinity of an equals 0? We've got to be a little more cautious with this one. What it says is that if this is true, the series may converge or diverge. We need further investigation. Now, I'll give you a couple of examples of that. Again, when we start finding out whether series converge or not, we want to take the limit of this thing. If it's not 0, we can immediately say diverge. If it is 0, we got to think about something that we got to figure out. It has a chance to converge. Let's see if I wrote that down here because that's really what I want here. Yeah. If it's equal to 0, the series has a chance to converge. If it was non-zero, it has no chance. Okay. So let's look at a couple of examples here. If I looked at this first one, the sum as from n equal 1 to infinity of 1 over n, guys, that's the harmonic series. We already talked about the fact that that one diverges. Harmonic, it diverges. Even though, notice, even though the limit as n goes to infinity of this thing was 0. Okay, I mean, it had a chance. It didn't last very long. So in that first one, the limit as n goes to infinity of 1 over n equals 0 just told me it had a chance. When I looked at it a little closer with my proof yesterday, I found out that it did not. It diverges. Look at the second one. If you let n go to infinity in this one, it goes to 0. But you look at that, that's that telescoping series we did a minute ago. Notice it converged. So I'm telling you, if it goes to 0, you don't know anything yet. Well, you do know something. You know it has a chance to converge. You know it has a chance to converge. If you look at this third one, and there's the AN, and you have the limit as n goes to infinity of this thing. We did those in calculus. That's 2/3. It's not 0. If it's not 0, right off the bat, you're done. It diverges. You go on. So one of the first tests we're going to use on convergence and divergence of series is to see if the nth term goes to 0. If it doesn't go to 0, we're done. It diverges. Okay. So the next thing. This is where I got in kind of a hurry yesterday, so I'm going to state the theorems and talk to you about what they say. And I also wrote the theorems out in a little more street language, I guess you'd say here. This one says, if AN and BN are series whose terms after some point in the series are the same, then both converge or both diverge. All right. You look at this one right here. On the very first day we talked about telescoping series, we found out that that thing converged to 1. It was telescoping, it converged to 1. Now, to address Alexa's question again, notice this is something that can be split up using partial fractions. That to me thinks, maybe this is telescoping, okay? That's what you're looking at there. So it converged to 1. Notice that its terms look like 1/1 times 2. It's 1/2 times 3, and so on. Now, let's look at this one. If you look at this one, if you start at, the series looks like 1/n plus 2 times n plus 3. If you put 1 in, you'll get 1/3 times 4 plus 1/4 times 5 plus 1/5 times 6. Now notice that those two things look exactly alike. That one, right, this one, the second one, looked exactly like that one right there. Okay? So, so what it says is they either both converge or they both diverge, because this one looks the same after a point that one does. Okay? So we know that by this theorem, this thing converges. Now, I'm not going to make a statement about this yet, about what it converges to. But you might think, well, if I left 2 terms off here and that one converged to 1, maybe it converges to 1 minus those 2 terms. And you might, and if you use partial fractions on this and found out what this one was, you might be able to show that. Okay? But if they look the same, eventually they look the same, it's not going to make a difference in the convergence. Okay?
Right. So is that like when they're combined, like when there's 2 of these?
Well, you would compare, actually, what your book asks you to do is say, it asks you to look at this one and say does this one converge or diverge? And then you're going to remember, well, I had one that looked like that eventually looked like that. So you're going to compare it to this one. It's really 2 different problems, but you might be just given this one, but you might remember that one and say, oh, well, it looks the same eventually, so both of them either converge or diverge. Okay? It's not the sum of 2 things, it's just individual things. I think if you look at your homework, you'll be able to see where these things look alike. All right, let's look at the next thing. Okay, the next thing says, if AN and BN are convergent series with sums A and B, then the sum of AN plus B, and this is when you add them together actually, then the sum of AN plus BN converges with sum A plus B, and the sum of AN minus BN converges with sum A minus B. Okay? If AN converges, then a constant can be brought out, and this thing will converge. C times AN will converge. In other words, you can kind of bring the constant out there, and the sum will be C times whatever's left, the sum, which will be sum AN, which is capital A. Now, let me let me show you what I mean by this one. Maybe, just maybe, you were asked this question initially. Maybe you were asked the sum from n equal 1 to infinity of -1 to the n minus 1 over 3 to the n minus 2 plus 1 over n times n plus 1. In other words, your series consisted of two things. What this thing says is that if we can show that both of these converge individually, then the sum will converge. We already looked at this one. I think we discovered that that one was geometric, with an R being, an A being 3. So the sum of that one was 3 over 1 minus a minus 1/3. That's the one we looked at a minute ago. Okay. We looked at this one. This one ended up being a telescoping series where its sum was equal to 1. So I was going to try to avoid fixing this fraction, but I'm going to fix it anyway now. That's 3. That's 3 over 1 plus 4/3. No, plus 4/3. Sorry, messed that up. It's just plus 4/3. 1 minus a minus 1/3 is 4/3. The sum of this other one was 1. So that's 9/4 plus 1. Ugh, this thing's not writing well today. 9/4 plus 1. And then 9/4 plus 1 will be 13/4. So that's what that one converges to. So if both of them converge, all right, then, and you know the sum, the whole thing will converge, and you can find the sum by adding the individual sums. That's all it is. If that were a subtraction, I would just subtract here. Works for subtraction too.
So is this like the limit, or I'm just confused like what the sum is? Like
the sum is when you look at all those let me see if I can show you something back here. The sum is when you look at, if you look at these individual sums, there's the first term, 1/3. There's the second term, 1/3 plus a 15th. There's the third one, 1/3, 1/15, that. If you look at these numbers, if that sequence converges, if that sequence right there converges, these are partial sums. If that sequence converges, then that's what we mean by the series converging, okay? But we can't always look at all of those. We can't always tell what those are gonna do. So we're gonna end up with all these tests that tell me what happens. So, but that's what we're doing. We're taking that thing right there. And other, by the way, let me go back to where it was and see. I knew this one's a little hard to look at because it alternates, but I definitely knew that one had a chance to converge because that limit right there went to 0. That's what the limit of these individual pieces are going to tell me, whether it has a chance to converge or not. But when we talk about the sum of being whatever, 13/4, it meant if you wrote down the sequence of partial sums here, if you wrote down S1, then S2, then S3, then what would happen is it would be getting closer and closer to 13/4. That's when you keep adding on. When you keep adding on to that sequence of partial sums. Remember how we added on to 0.6 plus 0.06 plus 0.006? The more we added, the more it got closer to 2/3. That's what you're looking at right there. That's
so like, why do people care about that one number?
See, that one number can be, you can solve lots of different kinds of equations with series. We haven't done enough to do that yet, but you can, people use them to solve equations to, anything from sending a rocket into outer space to figuring out how to dig up a big hole and put something in it, okay? There are lots of equations that have series in them that we want to know the sums of. The problem here with me trying to tell you what it's used for is we're still trying to figure out how to learn to use the hammer, and we can't envision the house, okay? So they do have very, very big applications. Right now in differential equations is a study of the rate at which things change because they're equations with derivatives in them. and you can express derivatives and functions in terms of series. That also makes computing time faster, because it's faster to compute. I think I told you about this before, but if you look at a series that looks like a polynomial that estimates E, it's easier and faster to compute it using the polynomial than it is using E, okay? Long answer to a short question. All right, let's look at another one. All right, look at this one, guys. That 3 is a constant. What that theorem I just gave you said was that we could pull a 3 out in front. Because if you were to write the terms of this thing, every one of them would have a 3 in it. Because that's just adding things onto things. And they all have a 3, so I could pull it out. What did we say about this? What kind of series is that, guys? This whole thing right here. What kind of series is it?
Geometric.
Certainly looks like it's geometric. If n is 1, it looks like my a is going to be 4/5. And actually, I looked at this one before. And to get the next one, you'd multiply by another 4/5. So both a and r are 4/5. The sum will be a over 1 minus r. And my r here was 4/5. So a over 1 minus r. That's a fifth. Invert and multiply. If I multiply by 5, the 5s will cancel and I'll get 4. The sum of that, the longer you go out, the more terms you look at in that partial sums, that sequence of partial sums will get closer and closer to 4. And it, you know, it's not a bad idea to test some of these things out. Now, that's what I said the sum of this was. So this part. So what's the sum of this whole thing right here, guys? What's the sum? That's an equal sign right there, sorry. If I said that the sum of this geometric series right here was 4, what's the sum of the one that's multiplied by 3? According to the theorem, it's going to be what?
12.
It's going to be 12. Exactly. That's exactly right. It's going to be 12. Okay? All right, the next theorem that I got that was important from yesterday, this one. It says if AN is convergent and BN is divergent, then AN plus BN diverges. If you add two things together and look at it as a single series, and one part of it diverges and the other part of it converges, the whole thing diverges. The divergent part kind of takes over the reins, and it says, I can't get closer and closer to anything if part of this is getting bigger and bigger. So if I look at this, what do you know about the series 1 over n? Does it converge or diverge?
Diverge.
What's it called?
Harmonic.
Harmonic, exactly. It diverges. This one, on the other hand, ends up being geometric with an a of 1/4 and an r of 1/4. The absolute value of r there is less than 1, so the absolute value of 1/4 in that one is less than 1. It is geometric and it converges. So that one converges, that one diverges. What this theorem says is, whoops, sorry, both. It's got to diverge if you put them together.
So like, when we just say diverges?
Yes. Actually, your book, guys, I'll just tell you this. When we start getting into more of these tests, your book's going to put a D or a C. Diverge, converge. Okay? Guys, I wrote out the homework again here. I went back and checked to make sure it was the homework that I gave you on your assignment sheet on Moodle. And it was pretty much exactly the same. I wanted you to do the same thing today as I wanted you to do 2 or 3 days ago. Okay? So it's all there, but all that stuff's on Moodle.
I'm gonna do the homework tonight for real.
Yeah, for real. Okay, for real. How about starting it? That would be a good.
I'm gonna do it for real this time. Watch, tomorrow you're gonna be like, wow.
I mean, this.
Something backed up.
Yeah, this section is so important. I want to make sure you get the highlights, and then you get the highlights, you can do the homework. Okay.
I feel like this is the hardest thing I've done in my entire life.
This.
Yes. I don't like it. I don't like it.
You said that about integrals when you first started integrals. I remember in Calc 1. You said, I don't understand this substitution stuff.
I don't like
Now
this.
look. So there's
these
hope.
letters, like,
There's hope. Okay. All right. So, okay. So we got a new one to put on you here. And it's not hard to remember either, but it's part of something, a group of things called positive term series. Now, a positive term series is exactly what you think it is. It's a series that's just got positive numbers in it. So we don't have any of that plus, minus, plus, minus, plus, minus stuff, okay? It's a series. A series is a positive term series if the sum of AN is such that every AN that you get when you play this thing out is greater than 0. Okay, so all the terms in it are positive. Okay, so actually here we've already had an example of a positive term series. If I look at the sum from n equal 1 to n to infinity, n equal 1 to infinity of 1 over n, that was 1 plus a half plus a third plus a fourth. That harmonic series is an example of a positive term series. Okay, so we've had an example. Now, here's what I'm interested in looking at. Something called a p-series. And a p-series is defined to be this thing. The sum from n equal 1 to infinity of 1 over n to the p, which will be 1 over 1 to the p, and 1 to anything is going to be 1. You plug in a 2, you get 1 over 2 to the p, 1 over 3 to the p, 1 over 4 to the p, and so on. So tell me what my p is in the harmonic series, guys. What's the power I'm raising n to? What's my p?
1.
1. That's an example of a p-series with p equal to 1. All right. What about this one? If I did this one, the sum from n equal 1 to infinity of 1 over the cube root of n. 1 over the cube root of n. It's a p-series. Tell me what p is.
A third. Wow.
Well, let's do a little algebra here. Let's write it. How do you write that cube out for me? How do you write it without the radical there?
Next to the 1.
It's to the 1/3, isn't it? It's n to the 1/3. That's a p-series, and p is 1/3. All right, I'll give you an easy one. That's a p-series. What's p? 2. It's 2. It's just the power on, p is just the power on n. Okay, so here's a theorem about p-series, and I'm gonna give it to you, and we're gonna use it, and then I'm gonna try to give you a brief explanation of why it works. The p-series, the sum from n equal 1 to infinity of 1 over n to the p, converges if p is bigger than 1, and diverges if p is less than or equal to 1. So, guys, let's look at the ones we glanced at and see what we can say about them. Now notice, I haven't said anything about the sum of this series because it's not easy to find the sum. At some point, we only care whether it converges or diverges, and we don't care about the sum. How about the one we knew was the harmonic series? P was 1. Notice what this theorem says. It says if p is less than or equal to 1, it's going to diverge. Well, p was 1 there, so the harmonic series would diverge. What about this one? What about 1 over n to the 1/3? P is what here, guys, again?
1/3.
1/3. Is that greater than 1 or less than or equal to 1?
Less than.
Less than or equal to 1. That one right there is going to diverge. That one's going to diverge. Okay. What about this one over here? The 1 over n squared. P was 2. What's going to happen there?
1/3.
P is 2. 2 is greater than 1. It's going to converge. Okay. So we already had some examples. Let me give you some more examples. The one we just did, that harmonic, P was 1, and so what we knew is that it diverged. I'll leave this up here because can you see that, guys? All right. if P is 2. Now, it doesn't have to be a 1 there, because what we know is you can bring the 5 out, and you'll be looking at 1 over n squared. So multiplying the whole thing by 5 isn't going to change the convergence of it. Does it converge or diverge? We just looked at that one too.
Converge.
It converges because P's bigger than 1. This thing right here converges. 5 times it, multiplied by a constant, ain't going to affect its convergence. We saw that in a theorem a little earlier where we said, well, if AN converges, then C times AN is going to converge, or the sum of that. I'm going to rewrite this one. That's 1 over n to the 1/2. I'm going to go from 1 to infinity. What's the P on that one? 1/2. 1/2 is less than or equal to 1. Therefore, that one diverges. I don't know why I was hung up on these radical ones here, but this will be 1 over n to the 2/3. 2/3 is less than or equal to 1, and it diverges. Okay. All right. Let me show you the general idea of why this works, and then we'll call it a day. In case 1, if P is less than or equal to 0, in other words here, if I had 1 over n to the -2, if P was less than or equal to 0, if I rewrote that, it would look like n squared. What's the limit as n goes to infinity of n squared? Where's this go? It's going to infinity too, isn't it? Remember what we said? We had to, for a series to have a chance of converging, it has to go to 0. This one does not go to 0. So for all cases less than or equal to 0, this thing diverges. Okay. Now, if I put in a 0 there, n to the 0 would be 1, and the sum of 1 would be 1 plus 1 plus 1 plus 1, which was also not going to go to 0. So we've got that. So in other words, what I just said was if P is equal to 1, it's divergent. All right, if P is equal to 0, you would get 1 plus 1 plus 1. Now here's where it gets a little bit sticky here, but just follow me, guys. Just listen to me, guys. If P is not 1, if P is not 1 and it's bigger than, I don't know what I meant by that, but P is bigger than 1. Notice this. What's this look like to you guys? Does it look like anything from Calc 1?
The lower limit.
Lower sum, where I was taking the limit as n goes to infinity to see if this thing came to a limit, and that we said that was the area. That's just a function 1 over x to the p. I'm going to sort of talk about that here eventually as if it's 1 over n to the p. The other thing I want you to think about is, what if we wanted to know this sum, the infinite sum under this curve? We just did that because what we did was improper integrals. If we want to know what this summation is from 1 to infinity, we take an improper integral. So we replace infinity with t. We take the limit as t goes to infinity from 1 to t of x to the minus p. And again, this is the case where p is greater than 1, which means it'll drop it down into the denominator there. And then differentiate. I'll add 1 here and add 1 there. I'll take it from 1 to t, and when I put in 1 and t, I get this. By the way, I pulled out the 1 over 1 minus p here and just looked at this. If you look at this and p is greater than 1, 1 minus greater than 1 is going to give you a negative exponent, which will drop it into the denominator. And if it drops it into the denominator, for instance, if p were 2, 1 minus 2, it would be t to the minus whatever 3, t to the minus 2, that would go to 0. If I drop that down in the denominator, and in order for that to be a negative number, p would have to be bigger than 1. So we would actually have a limit there, okay? So if p is in between 0 and 1, then that's a problem, because if it's in between 0 and 1, this is a positive value on t, and as t goes to infinity, the whole thing's going to go to infinity. That's how we figure out how why this test works. Well, let me scroll up a little bit. So the integral from 1 to infinity of 1 over x to the p diverges, and so does that if, let me get rid of this here, if p is less than or equal to 1, and if it's greater than 1, it will converge. That improper integral will exist. So if that converges, so does the series. It's like summing things up. It's like we were summing those rectangles up. There it is.
Wow.
That's the only big result I added today. The rest of it was a recap of what we'd already done. You see that now, let me ask you this, guys. You got to be able to distinguish now between p series and, suppose I had 1 over n squared, and I wrote out the terms here. That would be 1 over 1 squared, 1 over 2 squared, 1 over 3 squared, 1 over 4 squared would be 16. You now have to distinguish. If I just gave you that and I said, is it geometric? Here's a quick check. How could you get from 1 to 1/4? What would you have to multiply by?
4.
1/4. Does the 1/4 give you 1/8? Again, 1/4 times 1/4 would have given you what? 1/16. You can see that this is not an example of a geometric series, okay? So p series are different from geometric series. So you're going to have to learn to sort of distinguish between the two. You can do that by writing out a few terms and saying, can I go from one to the next by the same r? Can't do that here. Can't do that. From here to here, it's 1/4. From here to here, it's 1/2, and so on.
So with P series, we just say P is this.
Yeah, this is what a P series looks like. It's if you can write it as some constant over n to a power. And if that power is less than or equal to 1, then it diverges. If that power is bigger than 1, it converges.
Okay.
Okay? That's all it is. Now, be careful. If you said, what does this one do? What does n to the -3 do? Well, you need to drop that down in the denominator so it looks like this. So that would be 1 over n cubed. Does that converge or diverge? P is bigger than 1, so it diverges. I mean, it converges. Sorry, I screwed up. It converges.
My brain just almost got.
Okay, sorry. You're adding this one thing on. So I did not put any homework with this yet because it's just the tip of the iceberg in the next section. So guess what you got to concentrate on? 11.2, and then getting me that quiz by tomorrow afternoon at 5. So I suggest tonight, do the quiz. I do not think the quiz will take you very long. Send it to me tonight if you want to get it to me ahead of time. And then start working on this homework. Tiara, you tell me bye or say hey? Okay, bye. Oh, you got a question? That's a bye, isn't it?
Yep.
Yeah, okay.
I have a question.
Okay, what?
Are we done with this series? Like, I don't want to do it no more. Are we done?
You don't have a choice. We are going to do this probably until the last 3 or 4 days of class. So put your seatbelt on and enjoy the ride. Okay? Get a positive attitude because it ain't going to go away. It's the last of the semester. It's almost, we've only got 3 weeks, guys. I'm going to spend at least 2 weeks on this, 2 more weeks.
Oh my God, exams.
Bye. Bye. We will leave on that note, okay? See y'all later.
Sarah, you didn't tell me about the exams.
Oh, don't worry about the exams. I'll tell you about that later. Bye. I'll tell you about that later, I promise. I'll make it work out.